In this section and next section, we want to use the mathematical tool we just learned from the last session to analyze the guiding mole in cylindrical metallic waveguide. And in this session, we'll first talk about TM mole in such a waveguide. So we always start from the z component of the field and then put this into Helmholtz equation to solve the expression of the mole field. So let's write down the expression for z component of electric field for a TM mole inside such a metallic waveguide. And then I'll use the separation of variable technique to get a solution along the phi direction. So now we just write down the solution phi of phi equal to a coefficient multiplying with cosine n phi, and this n is an integer which is the mole number along phi direction. And we also know that inside this metallic waveguide will be establishing standing wave along the r direction. So we pick up the solution for Bessel function j and n, but the solution involves a location where r is equal to 0. So we have to abandon this Newman function because this Newman function will diverge at r equal to 0. So this r of r now is just a simple expression, which is j n hr, and h is the eigenvalue of the Helmholtz equation. So let's put together these two solutions and write down the expression of the electric field along z direction, which is a multiplication of this Bessel function Jn and also cosine n phi. And now we have to put boundary conditions into this expression so that we can figure out the eigenvalue h. The boundary condition requires the tangential component of the electric field on the boundary at r equal to a equal to 0. So this means that when I put a into this h of hr into this Bessel function, then this jnha has to be equal to 0. Given this condition, I will be able to solve the eigenvalue of h. So once we know the boundary condition at r equal to a, the requirement is jnha equal to 0. Then we'll be looking for the zero crossings of jn, the Bessel function of the first kind of order n. So let's go back to this diagram where you can see j0, j1 on this plot. For example, if we pick up this n equal to 0, and we'll be looking for the zero crossings of the Bessel function of the zero order at this point where you have the first zero crossing. So x01 is going to be equal to 2.405, and this is going to describe a mole inside the cylindrical waveguide. But if we set this h of a to be the second zero crossing point, this is going to describe the TM02 moles inside the waveguide. And of course, you can choose n equal to 1 if you have some variation along the phi direction. And don't forget that this n is a mole number along phi direction. So if you choose the solution to be x11 equal to 3.832, so this means that you will allow the mole number along phi direction to be equal to 1. So by choosing the zero crossings for different Bessel functions, you'll be describing different modes inside the cylindrical waveguide. So suppose that now you choose the zero crossing point xmp, and you divide the xmp with a, then you will be getting an eigenvalue for the mole tmmp. And you also know that the h will decide the cutoff frequency of the waveguide. So I record an expression here for you to calculate the cutoff frequency of a particular mole. So suppose that you are looking for the cutoff frequency of TMMP mole, then you can just use this expression and then put this h to be a value of xnp divided by a to give yourself the value for the cutoff frequency of TM-NP mole. So if I give you a short summary, this n tells you the mole number along phi direction. It tells you the standing wave lobe along the phi direction for this n, and this p is the zero crossing of a Bessel function describing the mole field along r direction. So for example, if we pick up this value as the zero crossing to describe your mole, where x01 is equal to 2.405, then this is going to give you a cutoff frequency for TM01 mole. So let's continue this discussion. So let's just pick up the x01 in your analysis. So you start to look into the mole field associated with TM01 mole. So you set n equal to 0 into the mole field along phi direction, which gives you a constant in this expression. And then you pick up the zero crossing equal to 2.405 for this x01 and set it equal to HA. Then you can calculate the eigenvalue H from this expression. Just divide this 2.405 with A, then you'll be able to get this H value. With the known H value, then you can calculate the cutoff frequency of this TM01 from this expression. And remember that this x01 equal to 2.405 is the smallest number, or the closest is the number, the zero crossing closest to the vertical axis. So this means that this cutoff frequency for TM01 mole is going to be the lowest cutoff frequency for this TM cylindrical waveguide. And we call this the dominant mole inside this waveguide, because this eigenvalue is the smallest eigenvalue in the system when we talk about TM mole inside cylindrical waveguide. So if we have the field for the z component electric field, then one can calculate all the other fields given by these three expressions. And there's for this TM01 mole, we have electric field along z direction, electric field along r direction, and also the magnetic field along phi direction. And this is the field lines based on these three field components. And you can see that the electric field along r direction is perpendicular to this cylindrical surface, and the magnetic field only has component along phi direction. So you see those circles in this pattern. And right at the center of the waveguide, you will have z component electric field, because this is a TM mole wave inside this cylindrical waveguide. 所以呢，在这个小节里头比较简短，我们大致上了解到怎么去解这个 TM mole 的 mole field 然后呢，使用这个 Bessel function 来了解这个 cutoff frequency 的大小譬如说，在这个 TM mole 的这个mole field 呢，在这么一个圆柱状的波导里头，我们首先把它的这个 z 的方向上的这个电场呢，把它给解出来。那解出来之后呢，这里有这个Bessel function 里头有 eigenvalue h， 但是呢，去解这个 h 的时候呢，你就把这个边界条件放进来，因为 tangential component of electric field which is Ez has to be equal to 0 when you set r equal to a， 所以呢，当你写下这个r 等于 a 的时候呢，这个场要等于0。这时候呢，你就去检查这个 Bessel function 的这个图形里头的 zero crossing 的位置在哪里。那第一个 zero crossing 的位置对于这个Bessel function 来讲的话呢，是 x01。所以呢，这个值是最小值，所以呢，这个 h 的值也是最小值，所以你算出来的 cutoff frequency 也是最小值，那你就得到这个波导里头的 dominant mole 它的这个 cutoff frequency，还有它的 mode 呢是 TM01。那这是一个标准的解这个mode field 跟 cutoff frequency 的一个方法。那基本上等一下呢，你也会看到，当我们在解这个 TE mode 的时候，整个过程非常的类似。